Welcome to Organic Chemistry Chapter 6. Today we'll be doing alkyl halides, nucleophilic substitution and elimination problems. Okay, the first thing we need to do is draw the compounds and classify each compound as either a methyl, primary, secondary, or tertiary halide. So methylene chloride is just CH2I2, and that would be considered a methyl. Carbon tetrabromide would be CBr4, and that would be a methyl. That carbon is not connected to another carbon. That makes it a methyl. 2-bromo, 2-methylpentane. So let's draw pentane. 1, 2, 3, 4, 5. And then 1, 2 on the 3, we put the bromo. On the 2, we put the methyl. And then we look at this carbon that's connected to the bromine and say, how many carbons is this carbon connected to? Connected to 2. So that makes it a secondary. Iodoform, that is CHI3 iodoform. That would be a methyl because the carbon is not connected to another carbon. Okay, so let's do hexane. 3, 4, 1, 2, 3, 4, 5, 6. 2-bromo, 3-ethyl, 1, 2, 2-methyl. Okay, once again, we look at the carbon that's bonded to the halogen, and we see how many carbons is this carbon connected to? 1, 2, 3. That makes it a tertiary halide. Tert-butyl chloride, the tert-butyl group is this group here. We look at the carbon that's bonded to the halogen, and we say how many carbons is that carbon connected to? And it's connected to 3, so that would be tertiary, and that's what the tert means, tert-butyl. Sec-butyl chloride, so we need a sec-butyl group, so there's our butyl, and the chloride is coming off of the secondary carbon there. So that carbon is bonded to 2 other carbons, and that's secondary, and that's what the sec means. Okay, this one, ethanol, so that's ethanol, 1, 2, and then we have 2, actually, let's do this again. Okay, sorry about that. Ethanol, 1, 2, there's ethanol. Ethanol, that would have to be carbon number 1, so 2 is trichloro. So you have 2, 2, 2 trichloro. So that carbon is connected to one other carbon, so that would be a primary. Okay, so cyclohexane, 2-methyl, 1-chloro. When we have trans, so just make one go at you, the other one go down. And then we look at the carbon that's bonded to the chlorine and say, how many carbons is that carbon connected to? And we see it's 2, so that would be tertiary. Pentane, that's 5 carbons, 1, 2, 3, 4, 5. The 3, we have a methyl group, and the 1, we have a bromo, and on the 2, we have a bromo. So we're looking at the first carbon, and it's connected to one other carbon here, so that's a primary. And then we look at this carbon that's connected to this bromine, and we say, how many carbons is it connected to? And it's directly connected to 2, so that makes it secondary. Okay, on this problem, we are going to give the IUPAC name for the following compounds, and then once again, we're going to classify them as methyl, primary, secondary, tertiary. The first one here, we have carbon connected to CH3, there's our carbon, and then this CH2Cl. Okay, so what name is that? We find our longest chain. 1, 2, 3. So we have 2-methyl -1-chloropropane. And then we look at this carbon, and it's connected to the chlorine, it's connected to one other carbon, so that makes it a primary halide. Next compound, CH3, CH2, CHBr, CH3. 1, 2, 3, 4. That is 1, 2, 3, 4. That's our longest chain. 2-bromobutane. And then this carbon that's connected to the bromine is connected to 2 other carbons. So that makes it a secondary halide. This carbon, the longest chain, would be 1, 2, 3, 4, 5. So you have 2, you do these in alphabetical order, the substituents, 2-bromo dash 2-methyl pentane, because there's 5 carbons. And you look at this carbon that's connected to the bromine, and you see that it's connected to 3 carbons, so that makes it a tertiary halide. This compound here would be 1-chloro, 1-methyl cyclohexane. So cyclohexane, and you look at the carbon that's bonded to the chlorine there, and you see how many carbons is that carbon connected to? 1, 2, 3. So that makes it a tertiary halide. This compound here would be 1, 2 dichloro, and we have, we can make that 1-1-methyl cyclohexane. Now, this one we have to do RNS. The one before, just because it was written as dashes and wedges, didn't mean it was RNS, because if you look at this carbon here, you go out and then you finally meet. So this was not an asymmetric carbon. However, in this compound you have 2 asymmetric carbons. So now we need the R and S. So 1, 2, 3, and that would be clockwise. Clockwise is R, and you have the methyl in the back, so you would put in front of the name 1R, comma, and then we got to figure out what 2 is. So this is the second one. We have the chlorine is 1. This would be the second, 2. So 1, 2, 3. That's counterclockwise. The hydrogen's in back, so this would be 2S. So 1R, 2S, 1,2-dichloro, 1-methyl cyclohexane, and you have 2 halogens there. So the first one here would be a tertiary, so the 1 is a tertiary, and the second one here is a secondary alkyl halide. Okay, going to the next one here. Bromine doesn't have to be in the ring or in the long chain. 1, 2, 3, 4, 5, 6, 7. So this would be, our longest chain is heptane. And we have a 3-isopropyl. And then we have a 4-, and then you put comma, and you would say, you could say 1-bromo ethyl. And so you put all this together. Then you classify this as a primary. So that carbon would be a primary alkyl halide. Okay, the next one here we have 1, 2, 3, 4, 5, 6, 7. 7 is heptane again. And this is off the 5, so that'd be 5-cyclopropyl. And this would be 4, 4 dichloro. And then we have -1 iodo, heptane. And then you would classify the 4 carbon with the 2 chlorines would be those would be secondary alkyl halides, and the one with the iodine would be a primary. Okay, list the following carbocations in decreasing order of stability. So the most stable is going to be this allylic, and not only is this allylic because the carbon-carbon double bond sp2 sp2, but in the carbocation's sp2, so you have resonance. So if you were to draw a resonance structure here, it would look something like that, but that's also a tertiary. So this is an allylic tertiary carbocation. So this is going to be your most stable because of resonance. And then this is an allylic. So you see the sp2, sp2, and then this is an sp2 because of the carbocation. But this is an allylic primary. So allylic primary would be second. The allylic tertiary would be first, most stable. And then you have the carbocation. This is a tertiary carbocation. That would be third. And the secondary carbocation would be fourth. And the least stable would be the primary carbocation. So this is the least stable. Classify each compound as an alkyl halide, a vinyl, or an aryl halide. Okay, so the first one we draw this out kind of more in a line structure. The carbon, fluorine, CH3. So you can see that that's a double bond, and this carbon-fluorine bond is on an sp2 carbon, so that would make it a vinyl halide. Vinyl halides do not undergo SN2 reactions. Okay, the next one we have here, CH3, and this would be an sp3 carbon, and so that would be an alkyl halide. And that would be a tertiary alkyl halide. This compound here, carbon, CH3, and this has 3 chlorines. This would be sp3, so this is an alkyl halide. And it would be a primary. Here we have a secondary alkyl halide. This is sp3, so it's alkyl halide. This, the carbon-bromine bond is on an sp2 carbon. That means it's a vinyl. And these carbon halogens are on an aromatic compound. This is aromatic group, so that would be aryl halide. So the only compounds that actually do the reactions of alkyl halides are alkyl halides. So the halogen needs to be on an sp3 carbon. For each pair of compounds, predict which one has the higher molecular dipole moment. So you have ethyl chloride or ethyl iodide. For this problem, I think after looking in the book, I think the problem, let's make the correction, which one has the higher, I think what we want here is the boiling points, because we're talking about physical property. So you can go ahead and make that correction. Ethyl iodide would have a higher boiling point than the ethyl chloride. And the reason why is because iodide is a heavier atom than chlorine. 1-bromopropane versus cyclopropane. I think that also is a typo. Sorry about that. I think that should be bromocyclopropane. And in that case, it would be the non-branch, the 1-bromopropane would have the higher boiling point because it has more surface area. Cyclopentene. Once again, I think this meant to be bromocyclopentene. And trans-2-butene. Not sure what that problem was, so just don't do that problem. Okay, on this one, show how free radical halogenation might be used to synthesize the following compounds. So how are you going to make neopentyl chloride? So that's IUPAC name is propane 2,2-dimethyl 1-chloro. That's neopentyl chloride. Okay, in order to make this compound, you'd start with the alkane. So that would be this compound here. And in the last chapter, we learned that we can add chlorine and light, and we can do an initiation reaction, which creates the chlorine radical. And then we can do a propagation reaction, where the hydrogen will get abstracted. Each one of these are primary halogens, so they're all equal. And so the first propagation step, you're going to get the free radical here, and you're going to get the hydrogen chloride. And then your second propagation step, your free radical is going to react with another molecule of chlorine to propagate the free radical reaction and make the compound that you desire in the product here. And so that gives us our neopentyl chloride. Doing the same thing with the bromo butane. So here's butane, here's 2-methyl, this is 2-bromo. How would you make this? Well, you'd have to do free radical halogenation. It's the only way that you can really get alkanes to be reactive. And in this reaction, you would abstract the hydrogen from the tertiary carbon. So the tertiary halogen, this would be very selective, and you would only get one product here. Show how each compound might be synthesized by SN2 displacement of an alkyl halide. Okay, so the first reaction, you just make this a primary alkyl halide, and then you can react this with sodium hydroxide. This will do an SN2 reaction. This is your nucleophile. This is your electrophile, because that carbon is delta positive, and the bromine is delta negative. Your nucleophile, your sodium, is a positive, so the oxygen is a negative, which is a great, strong nucleophile, and your bromine is your leaving group. So this does an SN2 attack to give you the desired compound. Okay, this one's going to come from I'm going to make the sulfur here a leaving group. So this is your nucleophile. This is your electrophile. So we need to put that with a leaving group. Our nucleophile will be the sulfur. So you can just react that, and your chlorine is going to be your leaving group. This carbon is your electrophile, and the sulfur is your nucleophile. And then you get your compound. Here we have to make the ammonia our nucleophile with its lone pairs, and this is our electrophilic carbon. So in order to make this product, we just put a leaving group here. Bromine's a good leaving group, and you'd react this with excess ammonia. This compound here, this is your nucleophile. So that came from sodium cyanide. In your book, you have a list of a lot of nucleophiles. This carbon here will be your electrophile. So we'll make that bonded to a leaving group That will not work. So I'm going to say that you can't do an SN2 reaction for that because that would be a vinyl halide. This one here, this one's going to be an internal. So you want to break this one, make that your chloride, and that's your hydrogen. You can just basically make that a base. So if you did sodium hydroxide, this would deprotonate. Actually, you would need sodium metal, sodium metal. And then that's a tougher one, and that would do a cyclization. This one here, the nitrile here can be your nucleophile. So you just make that your nucleophile. Your electrophile then would be this carbon here. So we will react that with CH3, CH2, CH2, and put a leaving group on there. And this will then do an SN2 reaction to give you your product. This problem says, what does that say? Chlorocyclohexane reacts with sodium cyanide. Okay, so that's your nucleophile. Your carbon nitrile is negative because sodium is positive. Sodium's an electropositive metal. Your electrophile then would be this carbon here. It's slightly positive because the electronegativity difference between that carbon and chlorine. And then this is your leaving group. The chlorine's your leaving group. So this reacts in ethanol to give cyclohexane. The rate of formation increases when you add a small amount of sodium iodide. Okay, so what happens is sodium iodide will actually displace, whenever you see sodium, you make that plus. Iodide is negative here. That will do its own SN2 and will displace the chloride. This is an excellent nucleophile. Iodide is. It's also an excellent leaving group. So this is why the rate increases here and you get the product. Now, the other thing is the reason why it's an excellent nucleophile and an excellent leaving group is because it's so large and polarizable. Polarizable means that it's so big it has this big shell of outside electrons. So the valence shell electrons is this big old cloud out here of iodide, and it's big and large, and so it likes to be alone, and it also can be a great, excellent nucleophile. Predict the products of the following SN2 reactions. Okay, SN2 reactions. So you guys spot your nucleophile. Okay, we'll do that in red. Your electrophile, that needs to be, we'll do that in blue, and then your leaving group. So nucleophile is here. So you see you've got the negative oxygen. You always draw your nucleophile to your electrophile, and then your electrons leave. So what we have here is these electrons. Your electrophile then is this carbon here. So this is your electrophile. This is your nucleophile. So these oxygen goes here, and the chlorine leaves. Then you write your product CH3, CH2 oxygen bonded to CH2, CH3. And that is an ether, diethyl ether. Okay, so electrophile here is this carbon with your leaving group. It's your electrophile. Your nucleophile then would be this carbon. Sodium's positive. The carbon is a negative. The negative goes towards the positive carbon, and then the electrons go with bromine because that's your leaving group. And then you rewrite your product. CH2. This is your electrophilic carbon and your nucleophilic carbon. Okay, the next one, your nucleophile is this negative sulfur. That's a strong nucleophile. It's a negative charge. Your electrophile is this carbon here that's bonded to this electronegative iodide, which is your leaving group. And so the nucleophile electrons will attack the positive electrophile, and the leaving group will take those electrons, and you form this new bond here, where the sulfur is bonded to your CH3. This is called a thiol ether. Sulfur and oxygen behave similarly. Okay, here we have a carbon bonded to the chlorine, so this is your electrophile. It's slightly positive. Your nucleophile is this negative carbon here, and so it will attack that positive carbon. The nucleophile always attacks electrophile, and your chlorine is your leaving group. So when you rewrite this, you just rewrite what you see, CH2 8, and then this is CH2 and your nitrile, or your alkyne. Okay, so when we spot here, we see this is our electrophilic carbon. That's our delta positive. The bromine is our leaving group. This is a secondary. And then our nucleophile is this oxygen that's negative because sodium is positive. So this oxygen will attack from the backside this carbon, and the electrons will leave with bromine. And we redraw this. Nothing was touched here, so the CH3 remains there. Now, we have to do inversion of stereochemistry, so we see the bromines coming at us. In this case, the opposite, OH comes from behind. So make sure you get your stereochemistry in SN2. You get inversion. Here, this was different than your book, so it's okay. So just recognize that your electrophile is this carbon. Your leaving group is chlorine, and your negative nitrogen from the azide will come here, and chlorine will take those electrons. And so when you rewrite this, that would be your product. And then count your carbons, 1, 2, 3, 4. 1, 2, 3, 4. Okay, for each pair, predict the stronger nucleophile in the SN2 reaction using alcohol as your solvent. Okay, so between the two, when you draw this out, you'll see that nitrogen here, this triethylamine versus diethylamine. You do your Lewis structure, you'll see that this one is less hindered, so that's going to make it a stronger nucleophile because those electrons here are available to attack the electrophile. Okay, between these two you have dimethyl ether, and then you have sulfur. Excuse me. Sulfur is larger, more polarizable. Okay, it's right below oxygen. So that is larger, more polarizable. So those electrons are going to be able to really get in to the electrophile. So that's going to be your stronger nucleophile. Same thing here. Phosphorus is larger and more polarizable than the nitrogen. Between these two here, you have sulfur with a negative charge. When you're comparing two atoms that are the same, the negative charge is going to be a stronger nucleophile. Here you're comparing nitrogen with oxygen as your nucleophile, and this one, the nitrogen is going to be more stronger nucleophilic, and the reason why is it's less electronegative, so it's going to hold on to those electrons less. Here we have the sulfur compared to oxygen. is larger and more polarizable. This one here, we have, let's draw it out. So we got CH3, CH3, CHO minus versus CH3, CH2, CH2. Okay, so what you're looking at is you're looking at a primary, and this is a tertiary. So the primary is going to be stronger. It's less hindered. So it's going to be a stronger nucleophile. So we'll go ahead. And here, iodide versus chloride. Iodide is larger, more polarizable, therefore stronger nucleophile. Here we're looking at the SN2 substrate. Which one's better? This is your electrophile. Okay, so electrophile for SN2, you want it to be a primary. Primaries are your best, or methyl. Allylics are good. Benzylics are good. Okay, because the reaction happens at a faster rate because it's less hindered. So let's draw these structures out. 1 iodo, 2 methyl, and this is a primary alkyl halide. You need to classify these when we're talking about substrates. Or tert-butyl iodide. Okay, so this is tertiary. So primary is going to be better for SN2. The next one, cyclohexyl bromide versus 1 bromo, 1 methyl cyclohexane. This is tertiary, this is secondary. Secondary is going to be better. Let me circle these. There's that one, and there's that one. 2 bromo butane, or isopropyl bromide. This is tertiary. This is secondary. This one actually, even though the secondary, wait, I'm sorry, this is secondary, and this is secondary. This one will be faster just because it doesn't have the extra methyl group here. So those are both secondary. Isopropyl is going to be faster, slightly. Okay, here we have butane, 2,2, 1 chloro versus 2 butane. Now, believe it or not, even though this is primary and that's secondary, the primary will be slower. So it's a secondary because this group here is very hindered to get into this electrophilic carbon. And then the next one is iodo butane. Actually, I would go with primary on that one, so I'm going to take that back. Even though I would go with primary. I would go with primary. Just stick to the rules. Primary. Here, iodo butane. 1, 2, 3, 4. And 2 iodo propane. This one's primary. So primary over secondary is a better SN2 site. Okay, draw for a structure, Fisher projection of the following SN2 reactions. The first one, cyclopentane, 3 methyl, 1 bromo, and this is trans, so make one go up, one go down, and KOH. Okay, so this is your electrophilic carbon, this is your leaving group, and this is your oxygen nucleophile. This is a secondary. Okay, so this is a secondary, this is SN2, this is a strong nucleophile. Those electrons will come here and do an SN2 displacement. And the important thing here is that you have inversion of stereochemistry. So this methyl didn't change, but now your OH has to come at you. So this will be cis. Okay, so you have to have opposite inversion. Okay, here we have R bromopentanes, 1, 2, 3, 4, 5, 2 bromo. And if you make this come at you and you do your rules, 1, 2, 3, you'll see that that's R, so that's good. And this is your electrophile. That's your electrophilic carbon. Your bromine's your leaving group, and then you have potassium cyanide. And potassium gets a positive charge, so cyanide, nitrogen gets a negative charge. This is your nucleophile. So nucleophile will come and attack the electrophile. Bromine will leave with those electrons, and you get inversion of stereochemistry. So now you draw the cyanide going back. And you can check this to see here, 1, 2, 3. That would be R, but then the hydrogen's coming at you, so you'd have to switch this to S. So this went from R to S, and that sometimes works. Okay, so here we have our nucleophile is iodide, okay, and our electrophilic carbon is right here. The bromine is going to be our leaving group. So when you draw this in Fisher projection, you want just to draw the iodide on this side, and now your hydrogen will be on the other side. Here, sodium cyanide, or thiol. So the sodium is positive, your sulfur is a negative, that's a strong nucleophile. Your electrophilic carbon is right here. The bromine is your leaving group. Fluorine is too strong of a bond, it is not a leaving group. So now the sulfur is going to come in at the electrophilic carbon, and bromine is going to leave. And so when you draw this, you can just draw the best way to do this would probably just put your fluorine on top. You could draw this SH here and CH3 and hydrogen going back, and let's see if that changes. So let's go ahead and do 1, 2, 3, 1, 2, 3. So that's an S, and here we have 1, 2, 3, and that's an R, or that's an S. So then you'd have to do the stereochemistry the other way. CH3, SH, go ahead and keep fluorine there, and hydrogen. 1, 2, 3, that's R. So just show that that's inversion stereochemistry. Okay, here we have our nucleophile is the O minus, because we make sodium positive, and we find our electrophilic carbon is bonded to the bromine. The bromine's our leading group. Once again, we have Fisher projections, so we're just going to make sure that we draw this nucleophile on the opposite side. So, and then hydrogen on the other side. Here D is deuterium. It's just a heavy hydrogen. And our nucleophile is our nitrogen lone pair here. So this is our nucleophile. Our electrophile is connected to that chlorine, which is our leaving group. And so our nucleophile is going to come in here, attack that carbon, and the chlorine is going to leave. So when you draw that reaction, you want to show inversion of stereochemistry. So you could just see if we can do this like this, and deuterium coming at you, hydrogen going back. You can do your 1, 2, 3, that would be R, but R would have to go to S because deuterium's in back, so this is S, and then this would be 1, 2, 3, and that would be S. And would that show inversion? Maybe you need to redraw this to show your inversion. Put your NH2 coming at you, Deuterium, let's see, 1, 2, 3, and that would be R. Okay, choose the member of each pair that will react faster by the SN1 mechanism. Okay, SN1 always give you a carbocation intermediate. Carbocation intermediate. So when you're dealing with a carbocation intermediate, you tertiary are more stable, allylic are, and benzylic are. Okay, so you have to stable the carbocation. If you get a secondary, you have to keep in mind for rearrangements. So 1-bromopropane. So you're looking at a primary, always classify, okay, classify these alkyl halides versus 2-bromopropane. This is secondary, so 2-bromopropane will be the faster. This is the opposite of SN2 mechanism. 2-bromo to methyl butane, that's a tertiary, versus 2-bromo 3-methyl, that's a secondary. So tertiary will be faster for SN1. In propyl bromide versus allyl bromide. Allylic bromides, they have resonance. They are stable. They are more stable. So allylic bromide. Propane, 1-bromo, 2,2-dimethyl. This is a primary. Or 2-bromopropane. I would go with the secondary. The next one, iodo, so 2-iodo, 2-methyl butane, that's tertiary. Tert-butyl chloride, that's also tertiary, but iodo is a better leaving group, so it will react faster because it will leave faster. 2-bromobutane, the 2-methyl versus ethyl iodide. I would go with the tertiary over a primary. Propose a mechanism involving a hydride shift or an alkyl shift for the Savolysis reaction. Okay, so I'm just going to show you the hydride shift. So first thing we do in an SN1 is our electrophile, our leaving group leaves. Okay, so here we have a leaving group and it leaves. And when that happens, we get a carbocation intermediate. Classify the carbocation intermediate. This is a secondary. So this is showing you now our nucleophile, which is weak here. You always have weak nucleophiles when you're doing SN1 or E1. And this can come in here, and that's going to give you the first product we see. However, we can get a more stable carbocation because this one here is a tertiary position. So if one of these methyl groups, the CH3, took their electrons and did a shift, it basically is going to trade places with, let's draw that one there, and then the carbocation goes over here to this carbon. Now when your nucleophile, CH3OH, comes in, you get the next product. Okay, so let's look at the B. Chlorine will leave. So your first carbocation you get is this carbocation here. We classify that as a secondary. Now you see your weak nucleophile here, ethanol. If it comes in with this first one, you get this first product. The next product is a hydride shift. So this is a secondary, but if you just look at the neighboring ones. So you look at this neighboring carbon and this neighboring carbon. If it moves over here to the first top carbon, it's going to still be secondary, so that won't help you out any. But if it changes places with this hydride, ooh, don't do that. wrong arrow. If it changes places and you do a hydride shift, so the hydride takes its 2 electrons and goes over to that carbon, you switch places. So the hydrogen now is here, and the carbocation now is there. Now if your nucleophile, which is ethanol and it's weak, comes in, you get this product here. Okay, so iodide leaves on C, so let's look at that. We have this here. If our weak acetic acid nucleophile comes in, we get the first product. This is a secondary carbocation, but look at this. If we switch places with this hydride, we do a hydride shift, then we can get a more stable. So this switches places. The hydrogen goes over here. This is a secondary allylic carbocation. So now if our nucleophile from the acetic acid comes in, you get this product. Here, okay, so the iodide leaves, we get a primary carbocation, and so this is not going to stick around at all. It's going to rearrange very fast. So if the hydride here moves, you're going to get a hydride shift. And basically the hydrogen switches places with the carbocation, and then your nucleophile will come in. That gives you your first product. If you get a methyl shift, which you can sometimes get, this carbon there will take these electrons and move here, and this is what you get when you get ring expansion. And so then what happens is you get, instead of a 6-membered ring, you get a 7. 1, 2, 3, 4, 5, 6, 7. This is that bond right there, and you got your carbocation here, and then your ethanol comes in there, and you get that product. Okay, predict the compound in each pair that will undergo salicylisis more rapidly. Okay, salicylisis is an SN1 type reaction, or E1. So you need to think of carbocation. So that means tertiary, allylic carbocations. So when you draw out these structures, H3CH, so the CHCl. Is that drawn correctly? I think it's missing a 2 there. So put a 2 in there. And this one's a 3. So this is tertiary, and this is secondary. So tertiary will be more rapid, because that would support a carbocation, more stable. This one's secondary versus primary, so secondary. This is secondary versus benzylic. If it left, you get a carbocation here. This, if the bromine left, would be benzylic secondary. So benzylic, due to resonance, would be more stable. This one here is a primary versus a secondary. Secondary is going to be more stable. Here, iodide's going to leave. It's going to go faster. Better leaving group. Here you have an allylic secondary, and here you have a secondary. So allylic secondary will be faster. Give the salicylisis products expected when each compound is heated in ethanol. Okay, so you got to generate the salicylisis, you got to get the SN1, the carbocation. So bromine leaves, and you get the carbocation here at this carbon, and this is tertiary. So ethanol is your nucleophile. The electrons will come in there, and then your product then would be OCH2CH3, which is an ether. Okay, here, chlorine leaves. You get your carbocation. This is a tertiary. So then you have ethanol that comes in. And you get another ether. Here the bromine leaves. So you get your carbocation. Now this is a secondary carbocation, and you see if it goes here, if it traded places, that would be a primary, which isn't better. But if it went here, it'd be a tertiary. Tertiary is better. So it's going to switch places. You're going to get a hydride shift, and your new carbocation will look like this. And then your ethanol will come in as a nucleophile, and you will get this product here, that ether. Okay, the next one here, the bromine leaves. When the bromine leaves, you get a primary carbocation. That's over here. You could have a more stable one. There's no hydrogens on there, so it's going to have to do a methyl shift, CH3 with its 2 electrons. So you're going to have to change places with one of these. And now that's tertiary. So it went from a primary to tertiary. And so now your ethanol nucleophile will come in here, and your new product will be, let's see, I'll write this out. 1, 2, 3, 4, 5, 6, O, CH2, CH3. Several allylic halides are listed below. Draw the resonance structures of the allylic cations formed by the ionization of the following halides. Show the products expected from an SN once Savolysis and ethanol. This is kind of like what we've been doing. The bromine leaves, and then you have this secondary allylic cation, carbocation, and you're going to have ethanol as your nucleophile, and it's going to come in and form this ether. Here you have a primary allylic carbocation, and that would do a resonance. We're just really going to go with the major one. So that would do a resonance. My resonance arrow, the double-headed arrow. Now this would be an allylic secondary. So then the ethanol comes in and forms a substitution product, and you get this ether. Okay, here bromide leaves. You get this secondary allylic, and then the ethanol comes in, does the substitution, and you get CH2, CH3, and then let's do D. Make sure we have enough carbons, 1, 2, that's right, the bromine leaves, and 1, and this is so going to happen fast, this hydride shift, because it's a primary, and you can make a stable allylic carbocation, so this is a hydride shift. So you draw your little squiggly and write the hydride shift, and then that puts that there, and then your methanol will come in, and then your product would be the same product as you have up here. Show how the following carbocations are prone to rearrangements. The first one you don't have to do. The second one, this is a primary. You have a hydrogen there. So if you do a hydride shift, you're basically going to trade places with the hydrogen and the positive carbocation. And then that's a tertiary. This goes from a primary to a tertiary. When the following compound is heated in methanol, several products are formed. Propose the 4 products mechanism. So the first thing you want to do is heat and methanol. So go ahead and what if you have, let's do carbocation, let's do a primary. Are we going to have a primary? This is a primary, so let's just actually have the nucleophile coming in and this leaving. So if that's your case, you have OCH3. You don't have that. So therefore, that didn't happen. Okay? So you don't have any SN2. So you're going to have to generate your carbocation. So the first thing that happens is bromine leaves, and you generate a primary carbocation. If this goes ahead and does an E1, where then the methanol comes in and deprotonates, then you get this product here, which is your first product. If the next thing that would happen is a carbocation rearrangement, because the primary is not going to be stable at all. So then you have a hydride shift, and that hydride shift would look like this, CH3. This is a tertiary carbocation. Now, several things could happen here. The methanol could come in. This is a, so if your methanol comes in, then this would be an SN1 after the rearrangement, and you would get that product. Or you could go on and have a different type of carbocation shift, which is what you see when you get ring expansion. So this is ring expansion. You have a 4-membered ring here. Here you have a 5. So instead of a hydride shift, you'd have a methyl shift. And so that means this carbon here actually moves. And so you get, you can go 1, 2, 3, 4, 5. So you have 5, and that's carbon number 4. This is carbon number 5. This is 1, 2, 3. And then that would be a plus there. 5-member rings like to happen. This hydrogen here, methanol can come and deprotonate that, and you would get a E1, which is elimination, or you could get substitution, where the methanol actually comes in, attacks the carbocation. If that's the case, then you get this ether here. Okay, predict the elimination products for the following reactions. Pentane, 1, 2, 3, 4, 5, 2-bromopentane plus sodium methoxide. Okay, elimination products. This has to be an E2. This is a strong base. This is a strong nucleophile. And you have a secondary alkyl halide. So, oh, it wants elimination products. So I was drawing the substitution product, but it wants elimination. So E2, this is E2, is going to be stereospecific. So what that means it's going to take the hydrogen from the carbon next door, and I just go ahead and just draw the major one, the major product, and it's going to give you the more substituted alkene. So this is a disubstituted alkene. If it had taken the hydrogen from this carbon, because you got to look at the carbon that's bonded to the bromine, it can only either take from this carbon next door or this carbon, hydrogen. And it's going to give you the more substituted product. Okay, so 2-bromopentane and sodium methoxide, that's the exact same one, so let's just skip that one. 2-bromo-3-ethylpentane. Now, you got sodium methoxide, and we're going to do an elimination, so it's got to take a hydrogen. So you look at the carbon that's bonded to the bromine, and then you look at the carbons next to it. This has 3 hydrogens. This has 1 hydrogen. Because it can take this hydrogen, it will. And if it takes this hydrogen and pushes the bromine out, then you get a tri-substituted alkene. So you see this alkene has 1, 2, 3 groups onto it. That's going to be the more substituted. And the more substituted alkene is thermodynamically more stable. So it's going to be your major product. So I just really want you to draw the major product. Okay, so the next one is cyclohexane. And we have 1 bromo and 2 methyl. And they're cis, so let's put them on the same side. Now when you draw these, you're going to have to draw the chair. And you're going to have to put the bromine in the down position. And then here we can put the methyl in the down position. And the reason why you have to do that is because E2 is called stereospecific. Okay, so it has to abstract a hydrogen 180 degrees anti-periplanar to the leaving group. So what this means is your base, sodium methoxide, will take either this hydrogen or this hydrogen because it's 180-degree periplanar to the leaving group. See, if you look at this hydrogen and that hydrogen, that's 180 degrees. Okay, the other hydrogen is the one next door over here, and that's also 180. Now notice if it takes, remember I care about the more major product. If it takes this hydrogen and pushes the bromine out, then you have a more substituted. So then you change it from the chair to the flat drawing. You lose your stereochemistry there. Predict the E1 elimination for the following. Okay, so when you're doing E1, you got to think carbocation. Carbocation. When you think carbocation, you need to classify because you have to do the most stable, so you might have rearrangement. So here, where the bromine's going to leave, so let's just go ahead. And when that happens, you lose your stereochemistry on that carbon because that becomes sp2. Okay, elimination. So you always do a thing called Yatsev's rule, and that's going to give you the more stable carbocation. So then when you have, I don't know, if you have this in methanol or whatever, then your hydrogen is going to get abstracted from here. And so your Yatsev's rule, always with E1, is going to give you the more substituted alkene. And so it's this hydrogen here that is going to leave to give you the more substituted. So you have this carbon or you have this carbon to look at, but if you pick from this carbon here, you would have had a lesser substituted. So the more substituted, this is a tetra-substituted alkene. Okay, so here we have bromine leaving. Let's go ahead and do our carbocation. That was a secondary, by the way. Or I'm sorry, tertiary. Tertiary is okay. Okay, so let's do this. This is a secondary, but we can get rearrangement here. So if we do a hydride shift, so we switch places, and now we have a tertiary. And then you look at, are you going to take from this carbon, the hydrogen, this carbon, or this carbon? And you can take from either one of these, and you're going to follow the Yatsev's rule. So that would be your product, and that would be a tri-substituted alkene. Here, this bromine leaves, and you get a secondary carbocation. If you get a hydride shift, methyl shift, then you get, come down here, like that CH3, switch places here with your carbocation, and then this could take a hydrogen from this carbon, or from this carbon, and you want to take it from this carbon because it's more substituted, and it will give you the more substituted alkene, and that's a tetrasubstituted alkene. It's got 1, 2, 3, 4 groups. When 1-bromocyclohexene undergoes phospholysis in ethanol, 3 major products are formed. Give mechanisms for these 3 products. Okay, go ahead and make a correction here because that's wasn't drawn correctly. This should have been this compound here. Okay. So this is phospholysis, so you need to think carbocation, you need to think E1 and SN1, phospholysis. That means it's just in your solvent. You notice you don't have a strong nucleophile. Bromine's going to leave, and when bromine leaves, this is a primary allylic halide. So if you have ethanol that comes in, you're going to get this product. Call that number 1. Okay, that would be an SN1. If you get rearrangement, which you would, not rearrangement, but resonance structure, so the electrons go over to the carbocation. So this would be a resonance structure. So those are equivalent structures. Then you can have this hydrogen. So methanol can abstract this hydrogen, and you would get the elimination product you see here. That would be an E1. Or you can get a substitution. So if the ethanol substitutes, that would be SN1 after the resonance stabilized structure. And that would be this product. Under appropriate conditions, S1-bromo, 1-fluoroethane, here we go, reacts with sodium ethoxide. Okay, so let's draw this structure. Okay, so first of all, let's just draw this as S. So let's draw this here. And CH3. Okay, so let's see. Did we draw this as S? 1, 2, 3. 1, 2, 3. That would be clockwise, so R. And so I need to draw this again. So let's put fluorine in the back and hydrogen in front. Now let's see if we draw this. 1, 2, 3. 1, 2, 3. That would be R, and then R would be S because hydrogen is now in front. So let's work with that structure. And that would be our S. And our nucleophile then is sodium methoxide. Sodium's plus. There's our nucleophile. And this is our carbon electrophile. And bromine is our leaving group. Now, why is fluorine not our leaving group? Because the carbon-fluorine bond is too strong. It's such a strong bond that it causes a lot of environmental problems. If you want to read more about that, you can read about Teflon and a thing called OA, octanoic acid, FOAC. Very bad. Okay, let's draw the transition state of the product. This is what this question's asking us. So we have our nucleophile, and it's going to do a backside attack. So it's going to come in opposite of the leaving group, which is bromine, and then bromine is going to take those electrons. And so our transition state then would look like this. So bromine's leaving, so you have a dotted line there. And then you have a dotted line with your nucleophile. So this is our transition state. Now what's going to happen is you get inversion of stereochemistry. So we're going to have OCH3 here, CH3 here, hydrogen, and fluorine. And now what's going to happen here, though, if you do your numbering 1, 2, 3, 1, 2, 3, which is counterclockwise, is S will go to R. And so then that is inversion of stereochemistry, and it is consistent with SN2. And if this reacts to give pure S, 1-fluoro-1-methoxyethane, the question is, did I do this one right? Let's see. 1, 2, 3. Counterclockwise. S goes to R. I don't know. That's the way. Okay, for each reaction, give the expected substitution product and predict whether the reaction will be predominantly SN1 or SN2. Okay, so now we have combined SN1 and SN2. Before, they've been separated. So how do you know? Well, let's look. So we have 2-chloro, 2-methylbutane, and we have this acetic acid. Okay, acetic acid is acidic acid. Acid can stabilize a carbocation. Okay, so those are carbocation stabilizing conditions. We have a tertiary alkyl halide. Okay, so that's going to be carbocation intermediate. And we're talking about SN1 versus SN2. So this is definitely SN1. It stabilizes a carbocation. It's acidic. This is also a very weak nucleophile. So then this will come in and you get your product. OH3. Okay, so that's SN1. The next one, isobutyl bromide plus sodium methoxide. Okay, sodium methoxide, once you make sodium positive, you make oxygen negative. Okay, that's a strong nucleophile because you've got a negative oxygen, negative nucleophile. This is a primary alkyl halide. So this is definitely going to be an SN2. And you're going to get OCH3. So that's definitely SN2, strong nucleophile. Those are actually basic conditions. Basic conditions do not stabilize a carbocation. Carbocations need acidic conditions. The next question, see, we have a cyclohexane, we have iodo on one, and we have methyl on one, and we have ethanol. Okay, ethanol. Ethanol can stabilize a carbocation. It is a weak nucleophile. you have a tertiary alkyl halide. Iodide is an excellent leaving group. So you're going to get a tertiary carbocation. And then your nucleophile will eventually come in, attack that carbon, and you will get your ether. This will definitely be an SN1. You can't have one, you either have one or the other. Okay, so here we are, cyclohexyl bromide. This is a secondary alkyl halide. And you got methanol. Methanol is a weak nucleophile. Weak nucleophile, you have a secondary alkyl halide. Weak nucleophile, you're going to get a secondary carbocation, and then your weak nucleophile will come in, and this will definitely be SN1 because it can stabilize a carbocation. Unlike the very next one where you still have cyclohexyl bromide, which is still a secondary alkyl halide, but now you have sodium ethoxide. Sodium ethoxide is very strong nucleophile. The basic conditions will never stabilize a carbocation. So you can't get SN1. You can only get SN2. So this is SN2. Give the substitution and elimination products that you would expect from the following reactions. Okay, so now we got to consider SN1, SN2, E1, and E2. And I really care about the major. Okay, so here we have pentane, 1, 2, 3, 4, 5, 3 bromo, 3 ethyl, and we have heat and we have methanol. Okay, so this is weak nucleophile. We have heat and we have a tertiary alkyl halide. So we're going to go ahead and get the carbocation, and you're going to get a combination of elimination products. So you're going to get an E1, and just go ahead and what hydrogen are you going to take that, or what carbon? You can take it from either one of these and you get the same product. That's a tri-substituted Yates rule. Alkene is your product, or you can get substitution here, and if you get substitution, the methanol will act doing a Savolysis, and it will eventually go in there and you'll get this. My guess is you're going to get more of the alkene because of the heat than you will for the substitution. But it does say give the substitution and elimination. So yes, E1 and SN1 for both of those. Remember, you have one or the other. Okay, so here we have cyclopentane, 1 methyl, 1 iodo. This is a tertiary alkyl halide, and you have a great leaving group, and it's heated in ethanol. You have a weak nucleophile. Iodide's going to leave. You can get your carbocation here. It will be stable. So now you're going to get a tertiary carbocation, and let's go ahead and give you the elimination products. So we could take a hydrogen from here, from this carbon. It will take one from the ring to give you your Yates product, the more stable alkene, and that's going to be an E1. Your SN1 will be your ethanol comes in and does a nucleophilic addition, and you get this ether. And the last one, cyclohexane, iodo, 2-methyl, silver nitrate, and water. Water is your nucleophile. Okay, so here's the deal. Silver loves iodide. It will precipitate it out. It is always carbocation stabilizing conditions. So you just go ahead and generate your carbocation. That's secondary. You're going to get a little bit of, so the elimination could come from here. You'll get a little bit of that elimination here to make that alkene, E1. You can also get a little bit of an SN1 here. And so this is water. Water is your nucleophile. So in this case, you're going to get a water to come in and get an alcohol. That's the non-arranged, rearranged product. Okay, but you're also going to get rearrangement. So you're going to get a hydride shift. And now you can get a tertiary carbocation. And then if you get the E1 product from that, it's going to give you the same as this. That's going to be your major product. And then if you get the SN1, you'll get the alcohol here, which is a tertiary alcohol versus a secondary alcohol. Okay, predict the products and mechanisms of the following reactions. When more than one product or mechanism is possible, explain which are most likely. So you have bromohexane, one bromo. Look at that, that's a primary, and sodium ethoxide. So you have a strong nucleophile. You have a primary alkyl halide. This is going to be SN2 every day of the week. And what's your product going to be? 1, 2, 3, 4, 5, 6. There's your ether. Okay, the next one, 2-chlorohexane. And now you have sodium methoxide. So strong nucleophile. I think you're going to get some competition with an E2 here. So this hydrogen will probably be abstracted to give you the more substituted alkene. If you do get minor, you might get, this will probably be your minor. So this is definitely your major, elimination, but you could also get minor product of substitution, SN2. The next one, butane to methyl to chloro. This is tertiary alkyl halide, and you've got sodium ethoxide, strong base. With the tertiary, you're going to get only E2. So the hydrogen can come, it's going to give you the most substituted, but it is stereospecific, so it's either going to take from this carbon, or this carbon. It takes the hydrogen from this carbon, and your chlorine leaves, you're going to get your more substituted Yachtses product. That's going to be your major product there, and it's going to be E2. Okay, we're on the next one. 2-chloro-2-methyl-butane, heated in ethanol. Okay, so this is this is carbocation stabilizing, okay, because you got a weak nucleophile. You don't have basic conditions anymore, so you're going to get your carbocation. This is a tertiary alkyl halide, and once again, your major product will be an E2, E1, and that's also going to give you Yachtses product, which is the more stabilizing, and you're also going to get probably a little bit of substitution here. So that would be SN1. It is already the more stable carbocation, so you don't have to worry about rearrangement. Isobutyl iodide plus KOH, ethanol and water. So this is a strong base. You have a primary alkyl halide. So you're going to get, I would do an SN2. OH. And the last one we have here is cyclopentane. 1-methyl, 1-bromo. So we know this is a tertiary alkyl halide. It's heated in methanol. This is a weak nucleophile. It's going to be stabilizing. There's a tertiary carbocation. It's going to stabilize that. So you're going to get elimination, so that would be E1, and you're going to get SN1 where you get your ether here, OCH3. The last product here is substitution products of the following reaction. So these are Fisher projections, and this is a strong nucleophile, great nucleophile, and this is a secondary alkyl halide. So you're going to get backside attack, and with these Newman projections, you just draw the hydrogen now on this side, nitrile on this side, and so you can see here's your nucleophile. Always attacks your electrophile, and your electrophile is this carbon right here. You get inversion stereochemistry. Here we have strong nucleophile again, and so this is your nucleophile. This is your electrophilic carbon. So the nucleophile oxygen is going to attack that carbon, and the bromine is your leaving group. And you're going to get inversion of stereochemistry. So the hydrogen goes here, the OH goes here. Nothing else is touched, so you just copy that down. And the next one you have, oh, by the way, this is a secondary, right? Alkyl halide. Here we have a tertiary alkyl halide. We have a weak nucleophile. So these are substitution products. So I'm going to do an SN1. This is going to stabilize a carbocation. So the bromine's going to leave, and you're going to get loss of stereochemistry here. And then you can have the ethanol can come in either side. So you need to draw both products. One's going to be the ethanol here with the CH3 coming in on the same side. This is going to be a top bottom. And then you can draw your other product where you have your ether OCH2 CH3 where your ethanol came in on the other side. And this is a racemic mixture. So you know that it will rotate plane polarized light 0 degrees. That is the end.